Hi, my name is Mary Napolitano, and I'm a product manager here at Standard Imaging. Today I'm going to talk a little bit about Effortless Plan QA with LinacView. So let's go over a bit of housekeeping before we get started. Today's webinar will be recorded. Please enter questions at any time during the presentation in the GoToMeeting dialog box. I will answer all questions at the end of the presentation. Standard Imaging is based in Middleton, Wisconsin, and founded in 1989. At Standard Imaging, we design and manufacture a full suite of QA products. So I'll start with going over some new features in LinacView, and then I will move into an overview of the basic workflow and background of log files. I'll touch briefly on comparing the information in RT plans and log files, and how we can use those parameters to generate fluence comparisons for specific plans. And finally, I'll touch on some interesting items in some recent publications. So what's new in LinacView? Version 3.11 was officially released on October 6th. The main features include the automatic generation of RT plans, reports being attached to the fail or alert emails, improvements in log file linking, RT plan generation improvements, and use of the modulation complexity score to specify acceptance criteria. So what does this all mean? I'll go into some more detail as I continue through the presentation, but I'll give a short description here. The automatic generation of RT plans is something that our users have been interested in, because you could go in and manually export an RT plan if you wanted to look in particular detail at a particular fraction delivery. But then we change that up so that RT plans are automatically generated based on the configuration that the user provides for up to each and every fraction delivered on the Linac. And then our users have also asked for reports to be attached to the failure or alert emails. That way the users can go ahead and get additional information without ever going into and launching the software. We have other improvements in the log file linking and the RT plan generation, because this is varies by Linac, and I'll go into some more detail concerning the log file linking. So with that, let's go on and take a look at the basic information workflow of LinacView. So everything, of course, begins here at the treatment planning console where the RT plan is generated. The RT plan is then exported both to the LinacView computer as well as through to the Linac console. And once LinacView has the RT plan in the system, then the log files that are generated when the RT plan is delivered automatically synchronize with the RT plan, and the analysis as is configured in the software either provides a pass, which is visible in the software, and or alternatively, if there is an alert or a failure of the delivered plan, then an audible alert will occur on the computer if you have it configured that way, as well as emails being sent. And this was the point where I mentioned that one of the new features is having a PDF report attached for these alert and failure emails, so that the physicists, even if they're off-site working, they can go ahead and right away get additional information about the plan. In addition, I wanted to mention that LinacView can also export RT plans. That can be done manually on a case-by-case basis, or one can configure that to occur automatically so that the log file generated RT plans occur with each and every fraction delivered. And then so one can set up in their clinic different workflows if they would like to send those RT plans via a scripting mechanism back into their treatment planning system. You can see on a fraction by fraction basis within your treatment planning system what differences may have occurred during the delivery other than what was planned. Or alternatively, one can send those automatically generated RT plans to an independent dose calculation engine. I would say that one of the advantages, though, in calculating back in your own treatment planning system is that you're separating sources of errors, because in the delivery, you want to be QAing the delivery itself. You don't want to be QAing your beam model or your algorithm. And so if you're using your familiar treatment planning system, you will have your commissioned beam model, you will have the algorithm you're accustomed to looking at, and so you won't be pinpointing errors associated with those mechanisms, or, for example, the ROI generation in your treatment planning system might differ from that in an independent dose calculation. And those are not the type of items that you will be doing your QA with. You will want to have a well-commissioned system before proceeding with your log file QA. So log files, they were initially generated as log files are for any software to record the delivery based on the feedback mechanism designed into the LINAC. Things such as the monitor unit and MLC positioning are assessed by the LINAC, and of course, if they're out of tolerance, you'll get DMOFs or a decrease in the dose rate. And so, it's not a perfect system. There is expected to be some variation from the plan, clearly. And so, but trying to determine, for example, how many leaves or how many segments with different monitor units variation still within LINAC tolerance can be clinically significant. And we could talk about that topic quite a bit more. But I'll just move on. There are different types of log files. The Varian, of course, has their clinic series has a Dynalog file. The TrueBeams have a trajectory log file. They both have different sampling rates. And then as well, the Elekta Linacs, we pick up and generate log files from the ICOM VX data stream, and that data stream is generated at 4 records per second. So then we gather these log files, and what exactly are the parameters that can be monitored? So we've touched on a few, like the MLC positions and the monitor units. Of course, there's also jaw positions, carriage positions, gantry and collimator angles, table positions and angles. But most important for us are these MLC leaf positions and fraction of total monitor unit, because we can generate a delivered fluence, your typical fluence map. And not to state that the table positions, angles, gantry, and collimator aren't important, because those clearly are important as well and should be monitored, but they are monitored separately than the fluence comparisons. And so we've determined that we can use the log files to generate a fluence map, but then there is some it takes quite a bit of logic and consideration to map those log file records to the RT plan control points. So in the treatment planning system, of course, you're all familiar that the RT plan uses control points and specifies the leaf positions at particular control points and the monitor unit. And so, but between those control points, what's really going on, and the log files open up that area and allow the physicist to see what is actually going on. And as we can generate these RT plans based on the log files, you can have more control points if your system will allow it, so that you can get more granular detail about what's really going on during the delivery. I would say the log file mapping varies, and it is dependent on the log file type. For example, the Dynalog file contains no control point mapping, but the trajectory log file, on the other hand, is much easier to map and match the RT plan control points, because it has direct fractional control points specified within the log file. And I think I stated previously that, of course, between control points, we assume, as does the treatment planning software, that the leaves move uniformly between control points, and that the monitor unit is delivered uniformly between control points. So I wanted to show you some screenshots of what one can actually see, and the way that you can use the software to investigate further. So I'll just go ahead and bring LinacView up, and this is the software. And this is for the particular plan that I had the screenshot up for a moment ago. This is a complex plan. It has a modulation complexity score of 0.07. And so that's fairly complex. Those of you that aren't familiar, a 1 is not complex, a 0 is very complex. And so you can just look, and we have a summary page here. It's color-coded. Red is areas that have failures, green areas that we have passing. We're, for this plan, primarily analyzing based on the fluence comparison. And so you can go ahead and move on over to this fluence tab, and you can see, your gamma histogram, the gamma index versus a percent fluence comparison pixels. You can see that the gamma has 92.9% pass rate at 2%, 2 millimeters. The mean gamma is 0.408. So both of these criteria met the failure that was specified by the user. And in this case, you have your gamma comparison map, and you can see these failing regions. And of course, you have your fluence maps below. And so what are the tools one can use? Well, you can go on over and review the leaves. You can see here that we're reviewing a particular leaf pair, number 10. You can review leaf pair number 11. And what you're seeing in this graph is the RT plan control point number versus the leaf position deviation. The red line is the failure. The orange line is the alert level. And you can see here that leaf number 10, which is which is bank B, everything's color coded. We can review just bank B, or we can review bank B and bank A together. But what you can see is that this particular leaf pair 10 is causing some issues. As well, one can look at the RMS error for the different banks, bank A versus bank B, and of course, dig in and look at all sorts of different statistics, review different leaf pairs, your maximum RMS error and maximum. Just a lot of information. We have a dynamic view that's really fun to look at. You can, play through and review your plan versus your fluence comparison throughout. So back to the presentation. Oh, yes. And the next thing I actually did want to show you, one more thing in LinacView, is that typically there's this batch dashboard. And for the most part, the plans come through, they are analyzed, and I've used my simulator to send a session in for analysis. And you can see that the session has been received. And so then the
alert
software,
alert.
If there's an alert, it will make this audible alert. And you can see as well that the RT plan has been exported and analyzed.
Alert.
You can see as well that we used a flag so that this is an electa complex plan. And so we can specify your gamma criteria based on the certain flags
out of tolerance.
And then, of course, if there's a problem, you get a different audible alert. And all this time, emails are being sent, which you can see over here in this column. It's just letting you know the emails are going out. And so it appears that ARC1 in general was a bit more complex than ARC2.
Alert.
And did have some delivery issues. And so then at that point in time, just from the dashboard, one could, take a quick look and see, for example, a few parameters, or one could go ahead and load this plan into the software and look like we did for the previous plan. But for the most part, you're going to see lots of passes. And I wanted to bring the PowerPoint presentation back up so we could just talk a little bit about those expectations. So how much workflow difference would this sort of log file analysis provide? So just real briefly, the fluence maps are created by projecting monitor unit weighted segments to the isocenter plane. And, with the passing plan, you're going to see something like a 99.7% gamma pass rate when we compare the RT plan fluence versus the log file fluence maps. And so that's what you'll see the majority of the time. And is this typical? Yes, it is. Good results are not surprising because you have already, commissioned your beam model, you've commissioned your LINAC. The comparisons are as fine as needed. There's no finite space detector grid to set up, no setup uncertainty. And so it's not surprising that for the most part, the plans are delivered as expected, as long as you're keeping up with your machine QA and maybe incorporating some log file QC into your program. But we do perform QA in order to catch the problematic plans, and they do occur. Even with the Halcyon, we have examples where we have picked up failures. And with that, I'd like to mention a couple recent publications. One is about using log files for automated patient-specific QA, in particular for Unity. And then another recent article that I don't have time to discuss, but it's a quality assurance procedure for trajectory log file validation. And so I point you to both of those, and I'm going to go into a bit more detail on this first one if you have a few more minutes to stay online. So in this particular journal article, 220 plans were delivered on an Electa Unity, and they were all analyzed using LinacView and measured with a commercially available detector array. And so if you're not familiar with the Unity, each and every day while the patient is on the couch, the plan is optimized for that daily treatment. So the traditional pre-treatment QA for the daily plan can only be performed after the fact rather than before. But LinacView can analyze immediately following the treatment. So in this case, what occurred is intentionally 30 of the plans were incorrectly matched to check for the error detection sensitivity. And using a gamma 3%, 3 millimeter for the 190 correct plans, the gamma pass rates range from 72.5% to 100%, or around 95 to 100% for LinacView. So this is the detector array versus LinacView. Since this was early on and during the commissioning phase, the detector array did find some commissioning problems with the Monaco couch, and that would not be found through the log files. So you must be aware of that, so that it's important to have your system commissioned prior to depending solely on log file analysis. But LinacView at the same time did find some MLC leaf parking position errors that the detector array did not find. But what's more interesting is these 30 incorrectly matched plans. And you can see here that the detector array had a gamma pass rate from 4% to 85%. So with this 85%, you might be uncertain as to how severe the issue was. LinacView had gamma pass rate between 0 and around 64%. And so the conclusion of this abstract was that significant rank correlation demonstrates that automated log file analysis can be used for patient-specific QA to expedite the adaptive workflow. And so a log file analysis is particularly important in these new adaptive workflow, both for the Halcyon and the elected Unity. It allows for ongoing patient-specific QA at a faster rate and allows for better throughput through this automation when you have plans changing on a daily basis. It's still important to get that QA in. So in summary, I hope I've convinced you that there's a wealth of information in your log files. I've given you just a little bit of information about how LinacView maps these RT plan control points to log file data. Certainly, if you have more questions, I'd love to discuss with you further. And then how we take that comparative information and do a fluence comparison with it. And next, that log file analysis is more sensitive in detecting errors compared to detector arrays. Based on the plan delivery. You can have a higher QA throughput because you don't have to take the time to deliver the plan again and set up a detector array. And LinacView version 3.11 has lots of new features, including auto plan generation and those reports included with the email alerts. So, thanks for your time and attention. That concludes my presentation. Please type any questions you may have into the dialog box. I don't see any yet. And so I'll give you just a few minutes and then I'll shut down the webinar. Okay, it looks like there's no questions. So if you would like to reach out to me later, don't hesitate to reach me directly through the Standard Imaging website. They can put you in contact with me, or my email address is mnapolitano@standardimaging.com. Have a nice day.